We've spent some time now talking about line integration, heat, and work, what those things are, and we've hinted at the fact that we might be able to do something useful using heat and work. And by useful, I mean in the practical laboratory sense. In particular, it would be really great if we could get work out of a simple system so that we could use it to do things in the world. This was actually one of the first things that thermal physicists in the modern sense were interested in. By the sort of beginning of the 19th century, and certainly by 1850, one of the main interests was how to create what are now called heat engines. This was in particular the preoccupation of one of the founders of classical thermodynamics, Sadi Carnot. So, what is a heat engine? Well, a heat engine should be some kind of simple system that uses input heat in order to produce work. Why is it that we need to have input heat in order to produce work? The answer is actually not too hard to see. Let's remember the first law of thermodynamics in its macroscopic form. Delta U is equal to Q plus W. Now, it's pretty obvious, I think, given everything that we've learned in the class so far, that typically increasing the internal energy will increase the temperature of a system as well. So if we don't want the temperature to go off to infinity, and we want to be able to operate the engine for a while, we probably want delta U to be 0, sort of in the long run, on average, for our heat engine. If that's the case, then the left-hand side here becomes 0. And so the right-hand side also needs to be 0. So we'll have Q is equal to minus W. Now there's a pretty simple way that we can do this, which is to make sure that our engine operates by taking the simple system through a complete loop. In a past video, we talked about the fact that anytime we have a line integral of an exact one form around a closed loop, we'll get 0. And so when we take du and integrate it over that loop, we'll always get 0. So that leads us to a motivating example. Here's a simple system, and I'll say that this is a monatomic ideal gas. We now have had a lot of time working with the monatomic ideal gas, and we know what coordinates describe it if we're talking about internal energy and work coordinates, U, V, and N. And the fact that we had those 3 coordinates when we were talking about all extensive coordinates means that any coordinate system we use will also have 3 coordinates. So here I've drawn a diagram of the cycle that we'd like to take this through in the coordinates P, V, and N, except that I think that N should just stay constant because we'll have a contained volume of gas through the whole transition, through this whole cycle. And so I haven't drawn N on the board to minimize the number of dimensions that I need to draw. All right, so what are we going to do to this simple system? Well, the first thing that we're going to do, and I'm realizing now I have this written in the wrong order, is an isochoric change, which I've labeled 1 here. Isochoric meaning equal volume. The second thing I'll do, once I've gone from P naught, V naught, this initial point, to PV, this final point on curve 1, is go along curve 2, which is isothermal. And that's going to take me from PV naught, up to P naught V. And we'll know that we're sort of at the end of that curve when we've reached our initial pressure, P naught. Finally, we'll do an isobaric change along the curve that I've here labeled 3. And that will take us from this point, P naught V, to this point, P naught V naught. And then we'll have completed a cycle, and so delta U will be 0. Okay, so if this is going to do work, notice from this equation that when Q or W is positive, then that type of energy is going into the system since it's increasing the internal energy. So when we talk about positive Q, that means that heat is going into the system. And when we talk about positive W, that means work is going into the system. If we want to be able to get work out of the system, then we want W to be negative. So let's go through and carefully check what happens in this particular simple system when we go around this loop one time. So first of all, we know that Q is going to be equal to minus W for a loop. So let's just worry about calculating W, and then we'll apply this in order to find Q. So to find W, what we'll do is we'll take a line integral over each of these three curves. The integral over different parts of a loop that's defined piecewise is just the sum of the integrals on those loops, so this totally makes sense. Furthermore, we know that W is the integral of minus p dv. So let's write things like this. So I'll say W is equal to minus p dv integral over 1 minus p dv integral over 2 minus p dv integral over 3. And I think that this basically makes sense as a style of writing these. So 1, 2, and 3 mean those curves. Good. We've also had some practice with line integrals at this point. And we've said that the way that we should often approach these is to try and find a coordinate system for each curve such that only one of the coordinates is non-constant on that curve. It turns out that for all of these, we're going to be able to do that, so let's launch right into it. For curve number 1, that's this curve. And here we have v is constant, and we also have n is constant. So that gives us two constants, and we could have, for instance, p as our third coordinate. But we also know that anytime this variable of integration, the one form that we're actually integrating over, which might be multiplied by a constant, anytime this one form is itself a constant, or the exact, what should I say, is the exterior derivative of a constant function on this curve, this is 0. So again, because v is constant on curve 1, this whole line integral is 0. Good. Now let's move to curve 2. We have that t is constant because this is an isothermal curve, and we also have n is constant. So now we just need to pick one more variable, or I should say one more coordinate, and then we're good. We have a full coordinate system. And it seems pretty clear that since the variable of integration here is v, v is a reasonable choice. So we'll do this in the coordinates tv and n. Lastly, for curve 3, well, on this curve, this is isobaric, so we have pressure being constant. We, again, always have n being constant. And so then we just need to pick any third coordinate to finish our full coordinate system. Again, since v is the variable of integration, let's pick v. So for this one, we'll do p, v, n. Okay. Now it's just time to rewrite all of these. So for the curve 2, we'll have this as our line integral. dv will be our variable of integration still, because v is one of the coordinates, so we don't need to re-expand this one form. We will, however, have to expand p, which we now think of as a function of tv and n. But what function is that? Well, we can use the ideal gas law to fill this in for ourselves. So we know that pv is equal to n kBt. And solving for p, that means that p is equal to n kBt over v. Good. So let's fill that in here. Furthermore, when we look at curve 3, p is one of our coordinates, but it's a constant on this curve. And what constant is it? That's very important. It's p naught. So we'll pull out a p naught, which is now constant on this curve. And this leaves us with just the integral over 3 of the exact one form dv. Great, so now we can make a bunch of simplifications. First of all, n kBt could come out here because n and t are constant on curve 2. That would leave us with the integral of dv over v on curve 2. Let's work that out down here. So the integral of dv over v is over curve 2, sorry. Well, now we can treat this just like a regular single variable integral that you will have learned about in calculus. So what is the antiderivative of dv over v? Well, it's log v. Then, because we're working on curve 2, we're going to evaluate this at the end point minus the beginning point of 2. So the end point here is v, and the beginning point is v naught along the v axis. So we get v minus v naught. Now that will end up being a difference of logs, but I can just make that the log of the quotient. So this is equal to log of v over v naught. Good. Okay, so next up, let's think about what happens for this curve 3. For curve 3, well, this is just, again, the line integral of an exact one form, so it's just the difference between the end point and the beginning point. So let's find that. So this is going to be v evaluated at the end point, which is v naught, minus the beginning point, which is v. So we get v naught minus v, but let's write that as minus v naught, where this quantity is in parentheses. And that will make our lives easier going down the road. Good. So let's do this. There's actually one more simplification that we can make. nkbt is constant, so it can come out of the integral. But that constant can actually be re-expressed in terms of p and v. And that's a good idea since we're working in PVN space in our diagram here. So once we pull this out of the integral, let me point out that we're going to do that first. Once we pull it out of the integral, we can then re-express it in terms of any point on curve 2, since nkbt is a constant on that curve. So we can take the value of PV at whatever point we choose, and that's going to be the same as nkbt. Now, what point should we choose? It's not immediately obvious, but after some thinking, we really have two options, p times v naught or p naught times v. And it turns out that p naught times v is going to make our lives a little bit easier here. So I'm going to say re-express this as p naught times v. All right, so once we do that, we get p naught times v times this integral that we've already worked out here, which is log of v over v naught. Then we get minus p naught times negative v minus v naught, so that flips the sign, plus p naught v minus v naught. Good. And let me bring down the fact that this is w, just for comparison in a moment. Now, based on this, we can immediately fill in what q is. Q is plus p naught v log of v over v naught minus p naught v minus v naught. Okay, so these are fine expressions. What remains is to show that w is less than 0 here, so that we're getting useful work out of the system. We'll know at that point that if w is negative, that q must then be positive, since q plus w is equal to 0, or q is equal to minus w, as I've written here. Okay, so let's make our lives a little bit simpler in trying to show that w is negative here. To do that, I'm going to introduce, so let me actually write what we're trying to show. That's always good. So we want w less than 0. So what I want to introduce is the compression ratio. And this is going to encode information about how much we allow the system to extend itself through this cycle. So I'm going to define this as phi, which is by definition equal to v over v naught. Good. Now let's rewrite w using this. So first of all, I'm going to pull out a p naught times v. Since p naught appears in both places here, and then pulling out v will allow me to write things in terms of the compression ratio. For this first term, I'll get minus log of, and then this is v naught over v, so that's just phi. So minus log of phi. Then for the second term, well, I'm pulling out a p naught v, so I'll get 1 here minus V naught over V, which is phi inverse. So I get plus 1 minus phi inverse. Okay, and I want to show that this is a negative quantity. What I'm going to do then is I'm going to define this log of phi as f of phi with no negative sign. And then I want to define this 1 minus phi inverse as g of phi. And so I get w less than 0 if and only if it must be that f is greater than g. I should point out that that's only true if both of these quantities are positive, but they are, as it's not too hard to show. So let's show this right-hand side of this equivalence, and we'll do that using calculus. So I first want to point out that the minimum value that phi can take is 0. And let me go back to my blue. Yeah, so the minimum value that phi can take is 1. And the reason for that is that phi is V over V naught. If we look here, we are trying to take this curve in this direction, counterclockwise. And so that will only be the case if V is greater than or equal to V naught, where equal to is sort of a marginal case. So this minimum phi is equal to 1 leads me to try to evaluate both f of 1 and g of 1. Now f of 1 is going to be equal to the log of 1, which is 0. And in fact, it's not too hard to see that g of 1 is going to be 1 minus 1 over 1, which is 1 minus 1, which is also 0. Good. Next, let's see what happens with the derivatives of these two functions. So f prime of phi, well, that is the derivative of log, which is phi inverse. Meanwhile, g prime of phi is the derivative of 1 minus phi inverse. The derivative of 1 is 0, and then the derivative of minus phi inverse, well, we'll pull down the exponent and multiply it by the minus sign. That will go to a plus sign, and then we'll reduce the exponent by 1, so it'll take minus 1 to minus 2. So this is going to be equal to phi to the minus 2. Good. I've already said that both f and g are positive, then they're exactly equal at the point phi equals 1. Then for all the points phi greater than 1, well, let's think about it. Phi to the minus 1 is going to be bigger than phi to the minus 2. So that means that f prime of phi is greater than g prime of phi. That combined with this leads us to the statement that f of phi is greater than g of phi for all phi greater than 1. Good. And that gives us exactly what we wanted. W is always less than 0. For all phi strictly greater than 1. Good. Okay, so what has this really shown us? It's shown us that this is a cycle that gets us some work if we put in some heat. Now, before we stop here, let's figure out where exactly we did work and where we got work back. And to do that, I first want to think about how we would do this cycle in a lab. So suppose that we have a system of a monatomic ideal gas that's contained in some kind of a piston that we can expand or contract as we want. Now we start that off at some initial pressure and volume. The next thing we do is we hold the piston tightly, and then we increase the pressure while keeping the, we increase the pressure while keeping the number of particles fixed. So we've fixed the volume by holding it tightly, and then we're keeping the number of particles fixed. The only way then to increase the pressure, given the ideal gas law, if we're not changing the volume and we're not changing the number, is we increase the temperature. So basically what we're going to do is hold this tightly and attach it to a hot reservoir. Then we'll allow it to heat up the system. Good. Next, we'll be at this higher pressure with the same volume. And so what we can do is now allow the system to expand. So we kind of take our hand off and allow the system to expand up to some maximum new volume. And we'll know that we're at the correct maximum new volume when we've reached our original pressure. So now our system is bigger, but at its original pressure. The next thing that we're going to do on step 3 is we're going to isobarically get the system back to its original volume. So exactly how would we do that? Well, one thing that we could do is if it's at, for instance, atmospheric pressure, is we could just open it up to atmospheric pressure. Now, how would we do that while keeping the particles in? It's a little complicated, but in any case, imagine that that's something that we are able to do. Then we just decrease the volume in that way. And the effect of this, since the volume is going from a bigger volume to a smaller volume, if we look at this equation, the volume going from a bigger volume to a smaller volume at constant pressure is going to lower the temperature back down. Good. So maybe one way we could think about doing this is that we're sort of allowing some, we're going to attach this to colder reservoirs or something like that. It's definitely easier to think about a pressure reservoir, but that kind of brings into question how we would stop the gas molecules from, or the gas atoms from escaping. All right, so whatever way we do it, we then compress back to our original volume. So now we think about this again. Again, we were heating up in this step, allowing to expand in this step, and then recompressing in this step. So it's pretty clear that heat is going to be coming in step 1. Heat will neither be going in. Oh, sorry. No. That is not true. And then at step 2, we're allowing this expansion. So that's where we're doing useful work. In step 3, we're going to actually do some work ourselves as we compress. But what this is telling us is that the work that we get out in step 2 is greater than the work that we have to put back in step 3. In general, it's going to be basically impossible to find heat engines in the real world where we don't have to do some work ourselves. Now, there's one final question I want to ask before we end this video, and that's, is this a good heat engine? And in order to evaluate if something is good, we need to have some criteria by which we evaluate it. Now, maybe you should just take a second and figure out what is your intuition about what would make a good heat engine. One thing certainly that people would think about is whether or not the engine puts out a lot of power. In other words, if we can do this kind of getting work out fast enough to be able to run something that we want to run. So for instance, if you want to speed up a car from 0 to 60 in a certain amount of time, then you need a certain power for your engine in order to do that. The problem with answering that question using classical thermodynamics is that power is going to be something like energy divided by time. So we need to bring time in to be able to do that. But thermodynamics is not a theory of dynamics. There is no intrinsic time variable that happens here. We're assuming that all of these processes happen quasi-statically. That means sufficiently slowly that these thermodynamic variables are defined for our simple system at all times. But there's no information beyond that about how fast this cycle is able to happen. So in order to answer that kind of question, we actually need a sort of more comprehensive theory, and we just won't deal with it anymore. The second question that we could ask, and I think that this one is pretty interesting, is something about efficiency. How much work are we getting out given sort of some other constraints? Now, we're going to talk a lot more about efficiency in the next video, but here I want to think about it in a very practical, sort of direct sense. We know that here we need to heat up the system in step 1, and we'll need to use some amount of heat energy to do that. Now, there will also be heat transfer in step 2, and it turns out in step 3. So maybe we need to figure out where we do care about heat transfer and where we don't care about heat transfer in order to say something like this. The idea, and I think that this kind of makes sense, is that in step one, that's where we actually have to go and get a thing that is hot, get a hot reservoir in order to put heat in. We typically think about the fact that in step two, there will be heat escaping, but if we're in an atmosphere, then that heat escaping, we don't really care about. It's just going to go into heating up the air around the lab. So in that case, we don't necessarily care about this. So maybe a good sort of prompt would be to think about how much heat do we have to put in step one in order to get the work that we get in the cycle. We'll answer that question and others in the next videos in this lecture. Until then, thank you so much for watching. See you in the next one.